Welcome to Automated Visual Software Analytics. This part is about 2.5-dimensional tree maps. We will describe the principles of 2.5-dimensional tree maps, explain their visual variables, and we will get an example of 2.5-dimensional tree maps. Let's start with the underlying problem, the motivation. It's about depicting tree-based data using graphical representations. In this example, you see a tree depicted by graphs. We have parent nodes and leaf nodes. All leaf nodes are colored. For each leaf node, we have a attribute data. For example, the K-log metric measures lines of code measured in 1,000 lines as a unit. The weight of a parent node is just defined as the sum of the weights of the leaf nodes. So this is a typical example of a tree data set, and now the question is, how can it be visualized? It can be visualized in a space-filling way using tree maps. If we depict it by a tree map, on the right side you see the corresponding tree map. We have nested rectangles. The root node corresponds to the outer rectangle, and the rectangles for children are nested within the rectangles of their parents. In this case, we also use a special tree map layout, the so-called scorified layout. So this is a mapping to a regular tree map. Now, what about a 2.5-dimensional tree map? 2.5-dimensional tree maps use cuboids. That means 3D blocks instead of rectangles. This way, 2.5-dimensional tree maps extend the tree map towards the third dimension. This example, the height difference is not too much, but we can immediately see the three-dimensional structure of the tree map representation. Let's define 2.5-dimensional tree maps. It's defined as a visual mapping of a tree hierarchy to cuboids. The ground areas of cuboids are nested on a root-ground rectangle in a space-filling way, similar to regular tree maps. The ground area size of cuboids is proportional to numerical weights associated with tree nodes, similar to regular tree maps. But the mapping is different. Each node of a given tree hierarchy is represented by a cuboid of the 2.5-dimensional tree map. The ground area of cuboids of child nodes is contained in the ground area of their corresponding parent node, and the specific tree map layout algorithm determines the spatial subdivision. The difference now is that cuboids offer an additional parameter, the height. Of course, they are also space efficient in a sense. In contrast to graph-based approaches, 2.5-dimensional tree maps efficiently use the ground area while extending the whole tree map to the third dimension. 2.5-dimensional tree maps are also called step trees, and the 2.5-dimensional, this expression comes from height fields used in geographic representations, for example, digital terrain models. We have a strong 2-dimensional base and a third dimension, but there's only one height value possible for each element of this 2-dimensional ground. For that reason, it's called 2.5-dimensional. Now, let's go on with visual variables. This is a key difference to regular tree maps. In regular tree maps, we have size and color as the visual variables where we can map information on these variables. In the case of 2.5-dimensional tree maps, however, we have an additional visual variable, the height of a cuboid. 2.5 dimensional tree maps offer also additional secondary parameters that can be used for information mapping. For example, we can use different cuboid geometry. For example, cuboids that have rounded corners or sharp corners. And also we can use the side and top faces of the cuboids and apply to them different textures. In summary, the visual variables offered by 2.5 dimensional tree maps are more flexible. They offer height as an additional strong visual variable, and they offer secondary visual variables such as cuboid geometry and face textures. Now let's explain this principle of 2.5 dimensional tree maps along this example. We see here a 2.5 dimensional tree map. Given weights are mapped to the footprint size for each rectangle. Next, let's add a mapping that defines the height. The height gets assigned a corresponding value, maybe taken from a software quality metric or from any other value associated with the tree hierarchy. And immediately we can see the three-dimensional nature of a 2.5 dimensional tree map. In the next step, we can use color as a second independent strong visual variable. Yeah, we can map another information onto this variable. For example, we can think of mapping code complexity on the height of a cuboid. So tall cuboids mean high complexity, coding complexity, whereas color can be used for editing frequency. So how fast do modules get changed? Of course, if we have a high coding complexity together with a high editing frequency, yeah, we can conclude maybe these modules are subject to errors or show a high error likelihood. Okay, so let's also use the secondary visual variables. For example, textures, face textures, in this example indicate the difference when comparing two versions of a software system. So in this case, it's a difference regarding the height variable, and it's outlined by a texture. This adds additional information. The 2.5 dimensional tree map gets more content, has more details in the visual depiction of the tree data. Yeah, let's also briefly come to the limitations. One strong limitation is occlusion. As cuboids are three-dimensional objects, depending on the viewing angle or the camera position in general, cuboids can occlude other cuboids if they are behind and smaller. For example, here we do not see that there is a cuboid behind, unless we use transparency to get still the right information. There are a cuboid behind. Approaches to overcome these limitations include to provide interactive 3D exploration and navigation functionality. That is, the users can directly change their viewpoint such that they get the right view or the right insights into the corresponding areas of a 2.5 dimensional tree map. We could also use transparency, maybe automatically set up, if cuboids occlude other cuboids. Summary. In this part, we have introduced 2.5-dimensional tree maps that extend regular tree maps towards a 3-dimensional representation. As a key advantage, they offer cuboids that allow for mapping an additional data attribute to the cuboid height. To depict a 2.5-dimensional tree map, typically an orthogonal view is used to avoid perspective distortion. 2.5-dimensional tree maps possess 3 strong visual variables: the size, the ground size of a cuboid, the color, and the height. Software analytics, in particular, can take advantage of these 2.5-dimensional tree maps for visualizing tree data, possibly even big tree data, because color and height serve as 2 independent information carriers, while a fixed attribute, such as lines of code, is typically mapped to the ground base size of a cuboid. So 2.5-dimensional tree maps can be used in particular to correlate 2 independent informations, one mapped to the color and the other mapped to the height. Of course, there's always a base information that is used for the ground size of each cuboid. Technically, 2.5-dimensional tree maps benefit from today's 3D graphics capabilities of common devices. They can be implemented in an efficient way using GPU functionality. For that reason, they can even be used to visualize big tree data. That is, 2.5-dimensional tree map rendering is scalable, which is very important for software analytics, because here we have to handle large data sets. Yeah, this concludes this part about 2.5-dimensional tree maps. Let's have a look on introduced terminology. We have introduced 2.5-dimensional tree maps, which define a visual mapping of a tree hierarchy to cuboids. The ground areas of cuboids are nested on a root ground rectangle in a space-filling way, similar to regular tree maps. The ground area size of cuboids is proportional to numerical weights associated with tree nodes, and the layout is calculated by a tree map layout algorithm, similar to regular tree maps. But color and height are 2 further and independent visual variables that can be used to map data attributes associated with tree nodes. Also, in the last sentence, there's a key difference to the regular tree maps. We have 2 independent, strong visual variables. As further reading, I can recommend the article entitled "The Design Space of Implicit Hierarchy Visualization as a Way which gives a broad overview of hierarchy visualization approaches." Yeah, finally, some remarks. We have seen 2.5-dimensional tree maps are, in a way, straightforward extensions to regular tree maps. They offer an additional strong visual variable, the cuboid height, for information visualization. 2.5-dimensional tree maps, if viewed from above using an orthogonal projection, practically are not faced by occlusion. That is, they have the same visual clarity and readability and even usability as regular 2-dimensional tree maps. Yeah, as a 3-dimensional visualization technique, they can be efficiently implemented on today's devices using the GPU processing capabilities. So they can be part of interactive visual software analytics tools. They do not demand for special capabilities or for special processing power. Typically, the 3D graphics capabilities serve to even visualize large hierarchies. For software analytics, 2.5-dimensional tree maps are essential, as they map and visualize tree data, offer 2 independent visual variables, color and height, to allow users to explore correlations, in particular to allow users to explore correlations between these two independent variables. So this is one of the core reasons why we like to use 2.5-dimensional tree maps in software analytics. There's another motivation, but it's not a strong one, to emphasize the hierarchical structure of the nesting of the modules, but this is more or less a side effect. So the core and primary motivation is to visualize two independent information dimensions.